I'm going to take you through the PHET sim, and hopefully you'll see how it and how these explanations will help you get a better handle on understanding solubility. So the first thing I'm going to start with is a situation where I've already loaded up some parameters into the sim, and what you should be seeing is a salt that is at its saturation point. So we're going to zoom in this particular area here, and we're going to listen for the concept of saturation point, and we're going to watch the movie associated with saturation point. Memorizing the words is no good if you can't see the movie in your head. So you should be seeing that there is a solid which is getting neither bigger nor smaller overall. Yeah, sure, the shape is changing, but the overall size of the solid isn't getting bigger, not getting smaller. And the way we describe that is we say the rate, or how frequently the particles are forming onto the solid, is pretty much exactly the same as the rate at which the solid is breaking up. You can think of that as like a sink that has the drain partly in, and so water's pouring out of a drain as much as it's pouring in, so the water level never changes. That doesn't mean that water isn't pouring in. It doesn't mean that water isn't pouring out. It means that the two rates are identical. So one of the other things we need to be able to do is describe this this phenomenon, play this movie in our heads, but also describe it in a series of pictures. And here are three different possibilities. Let me just zoom in on here, and there we are here. So possibility 1, 2, and 3. Possibility 3 is the one that we want. Notice that the size of the arrows in here we're trying to indicate that this particle is in the process of getting smaller and smaller and smaller. How do we know that? Because this big arrow says most of the particles are becoming aqueous. This picture says this particle is in the process of growing bigger and bigger, and we know that because this arrow from the aqueous phase to the solid is bigger. And this says things have pretty much balanced out, or it's at equilibrium, so however many are being broken away, that equivalent number is being formed. So this is the picture that we use for indicating something that is at equilibrium. Incidentally, were you to do this on a test, we would still want to see in here motion lines, Boltzmann's distribution, and all that other wonderful stuff. So let's just go back to our sim here, and let's try a new one. Let's go reset. We're going to take some of this water out just so the phenomenon is seen a little bit quicker. So we're dealing with table salt right now, and we're just going to do a little shake, and a shake, and a shake. So what we're looking at are those crystals that completely dissolved, so we're nowhere near the saturation point, and we're still nowhere near the saturation point. So we'll go clunk, and we'll put in some more. Okay, let's try this. I'm going to declare that I see a little bit of a solid right in here, but as I'm playing it, I'm seeing that for the most part the solid seems to be breaking up. But you know, the other thing I notice at this point is we seem to be just about the saturation point. I do see what I would call microcrystals, just temporarily forming and then unforming. If I add a little bit more sodium chloride, now I'm seeing a slightly bigger crystal, and I'll hit one more. And now I see things pretty much, well, actually that got a little bit smaller there for a moment, so that would have been an instant where this picture would have been appropriate. Okay, back to the sodium chloride and ignoring pictures and going back to the concept of solubility saturation point. So now I'm seeing that the crystal is pretty much staying pretty much the same size. Again, the shape's changing, no big deal. So if I add another crystal and hit pause, all of these particles, let's see, I've got maybe 8 green particles, and in the solid here I've got maybe 12. So what we should end up with is a solid that's about 20 particles, and notice that some of these are being obscured, so we're not going to be able to count them up. but what you need to be seeing is that the particle isn't, that when we did this, we added more solid, and more particularly, as we add this, we just keep on adding more solid. We're not actually adding more dissolved salt. So that's the other concept of this particular situation being at the equilibrium point. Insofar as driving that process is concerned, one neat way to look at it is think of this process as being primarily driven by these particles pushing themselves onto or into a solid arrangement. And you can think of this as this crowdedness as being a push or a measure of the push. So if we change the crowdedness, we change the amount of pushing, and now we get less solid formed. Okay, next up we're just going to do a quick little question and answer thing, play a little bit of math class with this problem, and we'll ask and answer the question. So what's the concentration of this salt solution in here once we have a saturated solution of sodium chloride? I know this is sodium chloride because I'm looking at this sim right up here. So let's take a look at the answer to that. So we're determining the concentration, and we've got to pick a temperature, and we're going to say for about 30 degrees, and we're going to augment our picture, or work with pictures. So our answer working backwards works out to 6.5 moles per liter. Still working backwards, we notice that there's a key piece in here, 38 grams per 0.1 liters. In here we see, in this section right in here, we see 1 mole per 58.5 grams molar mass of sodium chloride. No big surprises there. So let's just deconstruct this a little bit. In order to answer the question, what's the concentration there, what I need to do is I need to find the solubility in grams per milliliter, or grams per 100 mil. And funny thing, incidentally, on this is this graph says grams per milliliter, came off Wikipedia. This is wrong. It's actually grams per 100 milliliters. But anyway, so I grabbed this solubility curve. Even though it's a blue line and it looks straight, we still call it a solubility curve. I said arbitrarily in the question, let's do 30 degrees Celsius. So I found 30 degrees, tracked up here, tracked across here, and I'm going to declare this value in here to be like 38 grams per 100 mil. So let's go back to here, and that's where we got our 38 grams per 100 mils. Notice that there says 100 mils. So from the one standpoint, you could say the concentration is 38 grams per 100 mils, and that's absolutely right, but look at what the 38 grams refers to. We're talking about 38 grams of stuff that's floating around. We're not talking about 38 grams entirely. We're saying 38 grams are floating around per 100 mil. Right, okay, so back to our who's gonna do it here. Bingo. So there's a nice little kind of math question associated with this particular phenomenon. Now, I also said in that question we need to augment our answer in words and pictures, and we've already seen how to do that. We would draw a particle picture like this, and we would indicate some level of equilibrium being reached. So we would be using a picture like this to indicate 38 grams per mil. 6.5 moles per liter, and we would draw a big circle around here, and we would not include that solid, and we would indicate a circle or grab this piece and say that would be 6.5 moles per liter of stuff dissolved. Lastly, I'm going to take you through the sim where they deal with or let you show model slightly soluble salts, just because that can be quite instructive. So I'm going to start with copper 1 iodide. That's copper 1 particles. The most common copper particles are copper 2 particles, but we'll just use copper 1. And we'll add a couple of salt crystals here, and we're not at the saturation point yet. I know that because they all broke up. We'll add some more. I know it's slightly soluble, the salt, and I know that because I was told it was, but what I want you to do is see slightly soluble. Now if you go back into your memory cells or hit rewind or whatever, what I want you to notice is the concentration of the floating around stuff, the dissolved particles. So here we have copper iodide as opposed to sodium chloride. And notice how relatively uncrowded this space is. In the case of a very soluble salt, well, if it's very soluble, a whole lot of the particles dissolve. This only partly dissolves. So what we have is just kind of a, well, we don't have as concentrated a solution of free particles floating around with copper iodide compared to the sodium chloride. So what we should be able to do then is take a look at an example of something which is ridiculously not soluble. So I'm going to switch over to the Design a Salt section here, and I'll reset everything, and I'll pick a number. I'll tell you what, I'll actually model right here something that I know is really not very soluble, and I know that aluminum hydroxide has a 10 to the minus 33 KSP. So I'll go in and I'll model that particular salt using the sim, wherever the sim is. There's the sim. Great, so I know that the KSP is 1 times 10 to the minus 33. Is it 33? Yeah, it's 33. And I know that aluminums are plus 3, and I know that hydroxides are minus 1, so I'll model that. And I think what we'll do is we'll put in some aluminum hydroxide and we'll hit play. And we're dealing with something here that is at equilibrium. I know that because the solid doesn't seem to be breaking up. The free particles seem to be quote-unquote happy. And I noticed that a very small number of these things are floating around, and of course that's what we would call barely soluble. From all intents and purposes we would call that insoluble because there's so few particles floating around. And if we add some more right in here, are we going to get more particles floating around? And we're not going to get more particles floating around. Okay, so there you saw 4. Well, you saw 4 a moment ago as well. So we're not getting any more dissolution. We're not getting more unbounding. We're not getting more in particles in solution. We're still at equilibrium. We have a very, very, very low concentration of cations and anions, and that very low concentration suggests to us that this stuff is hardly very soluble at all.